Hello everyone, welcome to my presentation. My name is Yang Zhen. Today I'm going to present our work on non-asymptotic identification of linear dynamic systems using multiple trajectories. This is joint work with Professor Nani at Harvard University. Here is the outline of my talk. I will first give a short introduction on the identification of linear time-invariant systems. Then I will talk about system identification using multiple trajectories. In particular, I'll present data collection and the least square procedure for our method. I will also present a non-asymptotic analysis on learning Markov parameters. Finally, I will present some numerical results to demonstrate the performance of our identification method. I will end my talk with some concluding remarks. So in this talk, I will focus on the following linear time-invariant systems. Here, xt is the system state, yt is the system output, and ut is the system input. The system also has some process and measurement noise, wt and vt. The matrices A, B, C, D are used to describe the system dynamics. This model can be used to describe the dynamic behavior of many physical systems, such as autonomous vehicles, drone formations, and sensor networks. For the analysis and the control of these physical systems, it is very critical to have a good and accurate model to describe their dynamic behaviors. In some cases, a good system model can be built using first principles. In some other cases, we can collect some input-output data and perform some system identification procedure to get a good system model. And in this talk, I'll focus on model identification from input-output data. On a high level, the system identification has the following procedure. We first inject some control input ut into the system, and we measure the system response yt. From this input-output data, we aim to use some identification algorithm to estimate a good system model A hat, B hat, C hat, and D hat. And indeed, there are very rich classical results for asymptotic analysis, where we can guarantee the estimation is going to be very accurate if we have sufficiently large and infinite amount of data. In the past few years, people become very interested in finite sample complexity and non-asymptotic analysis, where we want to establish an error bound when the number of input-output samples is finite. One big motivation for this is to establish end-to-end performance guarantees of data-driven control systems. To build some non-asymptotic guarantees, the existing result typically leads to impose some assumption on the underlying systems. For example, some results require to directly measure the system state. If we have a direct measurement of the system state, that is yt equal to xt, we call the system fully observable. Otherwise, the system is called partially observable. For the identification of partially observable systems, many recent results lead to assume that the system is open stable. This means the spectral norm of the matrix A is less than 1. And unfortunately, this requirement is very restrictive. For example, here we have a very simple second-order system, which is obtained from a discretization of the Newton's second law. And this system has a spectral norm of 1. And then many non-asymptotic results are not directly applicable for this simple system. And in this talk, I'm going to present a simple least squares estimation procedure for the identification of a partially observable system. One key feature of our procedure is that we can deal with any open-loop unstable systems. And we also present a non-asymptotic guarantee for the estimation error. Now I'll move to the main part of the talk. So one key idea in our identification procedure is to use multiple trajectories of the systems. Here is some graphical illustration. Some recent results only use a single trajectory for identification. This might be very efficient for the case where it is hard to restart the experiment. However, in the analysis, we need to bound this error term, which in turn requires the system to be open-loop stable. Otherwise, this term becomes unbounded. And in our work, we considered the case where we can perform multiple experiments by resetting the system, and each experiment has a finiteness t, then every signaler is bounded in each experiment for both open-loop stable and unstable systems. And this setup is suitable for the identification of open-loop unstable partially observable systems. And this is the main idea of our approach. So, precisely, we aim to estimate the first t Markov parameter of the system defined as follows. And once we have a good estimation of the Markov parameter g, the classical whole common algorithm can return a good estimate of a hat, b hat, c hat, and d hat up to a similarity transformation. We also aim to provide a finite sample bound for the estimation error. As I mentioned before, we collect multiple trajectory YTI, UTI by injecting some IID Gaussian random input. The subscript T denotes the time step. The superscript I denotes the trajectory index. And each trajectory has a finite length T. In our work, we also make the following assumptions. First, the process and the measurement noise are IID Gaussian as well. And second, we assume we can reset the system at 0 initial state for each experiment. Now we can build an explicit connection between the input-output data and the Markov parameter g by expanding the dynamic equations recursively. If we connect all the measurements in one trajectory into one matrix, then we have the following expression. Here, g is the Markov parameters, w is the process noise term, b is the measurement noise term. Since each trajectory is finite length, the noise term have a zero mean and finite variance for both stable and unstable systems. This is an important fact to build a non-asymptotic bound. Once we have a multiple trajectory, it is very natural to use the following least squares estimation procedure. The solution to this least square estimation is also very simple, which can be computed as follows. And here, y and u are input-output data organized in the following form. In our work, we have derived the following non-asymptotic guarantee for the error bound. This upper bound depends on three terms. The first term is related to the measurement noise. The second term is related to the process noise. And the third term is related to the number of samples. And this bound is true for with high probability as known as the number of trajectories bigger than some constant. We have a few more remarks for this result. First, the estimation error scales as the order of 1 over square root of n, which is consistent with previous non-asymptotic result. Second, this result works for both stable and unstable systems, and the spectral radius of A can be any value. And finally, it is expected from the upper bound that unstable systems are harder to estimate since the process noise can be amplified during the dynamic evolution. In particular, we can see this fact from the constant C2, which grows exponentially when the spectral radius of A increases. And the proof of the result is not very hard. It follows from the standard non-asymptotic analysis of random matrices. First, it's very easy to see the error term can be written as follows, and from the standard norm inequality, we have this upper bound. Since the elements in U are IID Gaussian, the process noise W and input U are independent to the other, and also the measurement noise V and input U are also independent to the other. It's not difficult to derive these three bounds for this term individually. And putting them together leads to our final bound, which scales as the order of 1 over square root of n. And finally, I just want to highlight that the classical whole common algorithm can return good state space estimation as well, as shown in the following corollary. Now I will present some numerical results to demonstrate the performance of our least square estimator. We first consider a marginally stable system that corresponds to a discretization of the Newton's second law. We compare our method with the following two methods. The first method also uses multiple trajectory, but only the last data sample is used in each trajectory. The second method uses a single trajectory for identification, which is not suitable for open-loop unstable system. And this figure shows that the estimate error for these three methods when we change the experiment length t and the process noise level. It can be seen that our estimator, which is represented by the red circles, works for this marginally stable system and is consistently better than the other two approaches. And we next consider an open-loop unstable system. The result also demonstrate that our least square estimator has a better performance than the previous method, and our method is more sample shift efficient. And I'm now ready to conclude my talk. So the main message of this talk is that we show the multiple trajectory setup can easily deal with the estimation of partially observable systems that can be open-loop unstable. And in particular, we introduce a simple least squares estimator and provide a non-asymptotic bound on the estimation error. And for future work, it will be very interesting to derive low bounds for identifying general linear time-invariant systems, which may allow us to show the fundamental difficulty of unstable system identification. Also, it would be very interesting to combine our result with robust synthesis techniques and derive end-to-end guarantees for data-driven control. And thank you for your attention.